Good day. This is MTS 102. Today we are moving to section 2, which is limit of functions of free variables. Limit of functions of free variables. We have the objectives of the limit of functions of free variables here. Below are the overall objectives of it. That is, on completing this particular section, we should be able to define the limit of a function, determine the limit of given functions, state theorems on limits and apply them in determining the limit of functions, and also solve problems on limits. We have the content here, where we have the introduction to it, introduction to the limit of functions of free variable, get the definitions, calculation of limits, some rules on limits, etc. Moving to the introduction proper, in mathematical analysis, applications in geometry, applied mathematics, engineering, and natural sciences. The limit of a function is a concept in this course that we shall need to be very familiar with. The limit of a function is the value which a function takes or which it lies close to it. I repeat myself. The limit of a function is the value which a function takes or which it lies close to. For example, when s is very close to 2, f of s equal to s squared is close to 4. Means by the time you substitute the value of s into that function here, where we have s squared, the answer is 4. So it is very, very close to 4. We have the learning outcome mistake. Next slide. This is the definition of limits here. Definition of limits. The limit f of s is equal to L if s minus a for any positive number, however small, of a number delta greater than 0, such that modulus of f of s minus L less than epsilon, for all 0 less than modulus of s minus a less than delta, if there exists L, number a for which limit f of s as s approaches a equal to L, we say that limit f of s as s tends to a exists. However, if no limit f of s as s approaches a such L exists, we say that limit f of s as s approaches a does not exist. If limit f of s as s approaches a exists, it is unique. That is, if the limit f of s as s approaches a exists, then it is very, very unique. This without the solution. Let f of s be a given function. A number L is called the limit of f of s. That L, it is called the limit of f of s as s approaches s naught. That S approaches S naught is written as S tends to S naught in brackets. Now we're moving to the calculation of limits. Calculation of limits. Ability to calculate limits of a function is fundamental in calculus. Below are some methods by which this can be accomplished. That is how we can apply the methods, how the methods can be done. Then we move to the method of right and left hand limits. Method of right and left hand limits. When we say that the limit of a function f of s exists as s tends to s naught, we mean that the limit as s tends to s naught from all possible directions exist and are equal. When we say that the limit of a function f of s exists as s approaches s naught, we mean that the limit as s approaches s naught from all possible directions exists and are equal. Looking at this diagram, where we have a positive and negative side, then limit f of s as s tends to s naught positive equal to L1. That is the positive side, and limit f of s as s tends to s naught negative equal to L2. That is the left hand side. So we are now looking at this example for us to get better explanation. Then we have to find limit f of s as s approaches 2 if f of s is equal to s squared. Then we have the solution here. You notice that what happened here now, as we're solving that problem given, from the left hand side, so we pick the number that is very close to 2 from the left hand side, which is the negative side. We pick the number that is very close to 2 because the limit given there is as s tends to 2, s approaches 2. So the number that is very close to that 2 is 1.9, 1.99, 1.999. Let us now substitute that value into the function given where we have f of s equal to s squared. We first of all substitute 1.9, we have 3.61. We substitute 1.99 to where we have s squared, we have 3.9601. When we substitute 1.999, we have 3.99600. So we see here that approximately it is very close to 4, and we approximate it, the answer is 4. So we have been able to get the part of the left hand side. Then we move to the right hand side now, which is positive side. Then we now pick a number that is very close to 2 at the positive side, where we have 2.1, 2.01, 2.001. Here we substitute 2.1 to the function where we have s squared, and we got 4.41. Also substitute 2.01, we have 4.0401. Then we substitute 2.001, we get 4.00401. We then see that as s approaches two negatives, f of s tends to 4, and as s approaches 2 and the positive side, f of s is also close to 4. So we now see that both, as we apply the method of left and right hand side, we will be able to get the same answer. Hence, limit f of s as s approaches 2 on the negative side is equal to limit f of s as s approaches 2, the positive side is also equal to 4. So they're having the same answer. Therefore, the limit exists and equal to 4. So we've been able to establish that fact from the method of the right and left limits. Now we move to the limit of polynomial function. Limit of polynomial functions. For polynomial functions, y equal to an sn plus an minus 1 sn minus 1 plus 1 and 2 plus a1s plus a minus. You see that this is polynomial function. So it can be proved that limit f of s as s tends to s naught is equal to f of s naught. For example, find limit f of s as s approaches to where f of s is equal to 2s squared minus 3s plus 4. Here, we're going to substitute directly. That is, we use a direct substitution here. Let's have it. Since f of s is a polynomial, then we have limit f of s as s approaches to, which is equal to f of 2. This for substituting the value of s here, which is equal to 2 into 2 in brackets square. So anywhere you see x, just substitute 2 minus 3 in bracket 2 plus 4 is equal to 6. And we see that the limit exists here under the limit of polynomial function. So we move to the limit of rational functions. As you all know, as you have heard before, that limits of rational functions here is written as p of s over q of x, and rational functions is a fractional function. So it is in form of fraction here, where p of s and q of s will be algebraic functions. We factorize both the numerator and the denominator where possible and cancel out the common factors. So what we just said now, let's look at it in this example where we have a f of s equal to s squared minus 1 over s minus 1. Now to find limit f of s as s tends to 1. So here, looking at the functions given, it is in algebraic form. So the numerator is s squared minus 1 and the denominator is s minus 1. So we now factorize the numerator here, because as it is given, we can factor out the numerator. So we get the factors there as s minus 1 and s plus 1 all over s minus 1. Looking at it, see that s minus 1 cancel out s minus 1 at the denominator side. So we are left with s plus 1. So from here, you now substitute the value of s given, which is 1. Then substitute 1 where you find s. The answer is 1 plus 1, which is equal to 2. So That is for rational function. Then we move to limit of trigonometric function. Limit of trigonometric function. The limit of a trigonometric function depends on the specific function and the point at which the limit is being evaluated. The limit of a trigonometric function depends on the specific function and the point at which the limit is being evaluated. Let's look at this lemma. Let theta an angle measure then pay the limit sin theta as theta tends to 0 is equal to 0. Limit cos theta as theta tends to 0 is equal to 1. Then limit at tan theta as theta tends to 0 is equal to 0. So you can get that using your calculator. Then you see that by the time you substitute the value of theta into all these trigonometric functions, so you will be able to get all that facts. So you can try that. Then look at the theorem. The next theorem, which is where we have a limit sin theta over theta as theta approaches 0 is equal to 1. And 2. Limit tan theta over theta as theta approaches 0 is also equal to 1. So let's now move to the next slide. Let's move to the next slide. Then we have a limit at infinity. Limit at infinity. When we wish to examine the behavior of a function as s increases or decreases without bounds, we write s approaches positive infinity, or we write it as it is in the brackets, or s approaches minus infinity respectively. To evaluate limit as s approaches infinity in rational function, we divide each term by the highest index x and apply the lemma below or its variant. Look at this lemma. We have a let's look at it. Limit 1 over s as s approaches infinity is equal to 0. That is the fact there. So let's now look at this example where we have a find limit 2s squared plus s minus 3 all over 6x squared minus 17x plus 5 as s approaches infinity. So looking at this question here, so we have told that we're going to divide through by the highest index. That is where we have the highest power of x. Where we have the highest power of x. And what is the highest power of x here? It is s squared, s raised to power 2. So that is what we are going to divide both numerator and denominator with. We are going to divide the numerator and the denominator by x squared. So let's go on. We have the first value there. It is 2s squared divided 2s squared by s squared. We get 2. We divide s by s squared. We have 1 over s, and we divide that minus 3 by s squared. We have 3 over s squared. Then looking at the denominator, we have 6s squared. Divide 6s squared by s squared, the answer is 6. We move to minus 17s. Divide minus 17s by s squared, we have 17 over s, and we divide the 5 by s square, we have 5 over s square, which is equal to, by the time we now substitute the the limit given, by the time we substitute the limit given, then we have 2 plus, that is 1 over infinity will give us 0, minus 3 over infinity square will also give us 0, all over 6 minus 17 over infinity will give us 0, plus 5 all over infinity square will give us 0, and the answer is equal to 1 over 3. The answer is 1 over 3. So to the next slide now, we move to the continuous function. Continuous functions. A function f of s is said to be continuous at a point s naught if limit f of s as s approaches 0 is equal to f of s naught. That is, a function y equal to f of s is continuous at a point s naught if, let's look at this, the 3 points here. A function y equal to f of s is continuous at a point s naught if it's defined in a neighborhood of that point s naught. That is the one fact there. The next one, the limit of the function as s tends to s naught exists. If that limit exists, then we say it is continuous function. And also, this limit is equal to the value of the function at the point s equal to s naught. So all these 3 points, if we check and you see that the functions are continuous at that given point, we say that it is the functions exist and it is continuous functions. So let's check this example now, just to establish the fact we have been talking about. So f of s is equal to s all over s squared minus 2. F of s is equal to s over s squared minus 2 at s equal to 1. Then the other question, which is number 2, f of s is equal to 1 over s minus 1 at s equal to 1. So let's look at the solution one after the other at s equal to 1. So if we substitute 1 into this, so we're going to get minus 1. Looking at the next slide, so we substitute, we got s equal to minus 1. The first one, we know that f of s is defined as s equal to 1. So the next fact we substitute, then we see that the answer there is minus 1. We substitute 1 into where we have 8 and that of s squared, then the answer is minus 1 and the limit exists. And the last one, where we have the third fact, then we see that the limit s over s squared minus 2 as s approaches 1 is equal to f of 1. It is equal to f of 1. So therefore the condition are satisfied and function f of s is continuous at s equal to 1. It is continuous at s equal to 1. So let's look at the question number 2, where we have f of s equal to 1 over s minus 1 at s equal to 1. So firstly there, let's substitute the value of s to the function given. We see that the answer we got is infinity. So f of s is not defined at s equal to 1. It is not defined at s equal to 1. Here also we see at the Roman figure 2 there, that limit f of s as s approaches 1 does not exist at point s equal to 1. It does not exist. Since we have substituted and we see that we got infinity, it does not exist. And since one of the conditions have been violated, then f of s is not continuous at the point s equal to 1. We move to the next method, where we have a conjugate method. Conjugate method. Recall that the conjugate of square root s minus 5 is square root s plus 5. That is the conjugate of s minus 5 here. You only need to change when you are getting the conjugates, you only need to change the sign there. So where we have minus, you change it to positive. So the conjugate of square root s minus 5 is this square root s plus 5. Let us now look at this example where we have a limit square root s plus 11 minus 4 all over s minus 5. Looking at it here, the square root is not cover everything at that numerator, is only cover s plus 11, excluding the minus 4. So now when you want to get the conjugate of this, or you first, if I were you first of all apply direct substitution. Let's try direct substitution first, whether we are going to get the what the value we're looking for. So let's now check maybe it's the limit will exist. So let's try the direct substitution. By the time we substitute the value of first given, which is 5, substitute into that where we're having it, we have a 0 over 0, which is undefined, this indeterminate. So we now try the method here. Then you get the conjugate of the value here. Let's get the conjugate of square root s plus 11 minus 4. So what is the conjugate? The conjugate of it is square root s plus 11 plus 4. Where you see negative, then you only need to just change it to positive sign. So we now divide it through. It is a fraction. So you divide it by, you multiply by the conjugate. You multiply it by the conjugate. So we now have a square root s plus 11 minus 4 all over s minus 5 multiplied by the conjugate. You see it is in fraction. That conjugate, you multiply it, then you now evaluate. You evaluate. The time you evaluate, we now have you multiply that of square root s plus 11 minus 4 by square root s plus 11 plus 4. Then we multiply the denominator also, which is s minus 5 multiplied by square root s plus 11 plus 4. So the next, we got s plus 11 minus 16 over s minus 5 in brackets square root s plus 4, s plus 11 plus 4. So we move to the next slide. Then we now have s minus 5 all over s minus 5 in brackets square root s plus 11 plus 4. And the answer we got there is, at the time you divide the numerator here, you can see that s minus 5 at the numerator side cancel out s minus 5 at the denominator side. So we now have our answer as 1 over 8, because when you add the one inside the square root, that is, you might have substituted the value of x, which is 5, and you substitute it where we have x. That means we get 1 over 5, 1 over square root 5 plus 11, and square root 5 plus 11 will give us square root 16. Give us square root 16. And what is square root 16? Square root 16 is what? Is 4. Then we now have 1 over 4 plus 4, which is equal to 1 over 8. Is equal to 1 over 8. So that is the answer there, and you see that the limit exists. The limit exists. So next we move to the method of L'Hopital's rule. L'Hopital's rule. Now here, let y equal to f of s in R1 and y equal to a in bracket s in R2 be two functions, and let a in R1 intersect R2. Suppose that f of a equal to f prime of a equal to f prime prime of a equal to 1 and on to f into k minus 1a, which is equal to 0. G of a equal to g prime of a equal to g prime prime of a equal to 1 and on to g of k minus 1a equal to 0. F of k and g of k are continuous over some intervals. T so S subset of R1 section R2 which contains a if g k of a not equal to 0. Then we have limit f of s over g of s as s, which is a, which is equal to f k of a and over g k of a. So here L'Hopital rules establish this fact, that is f of s is the numerator and g of s is the denominator. Here, when you are given any question under this, then we apply the L'Hopital rules. How do we do that? By the time we substitute the value of the limit given here, for example, where we have evaluate limit s minus sin s over s raised to power of 3. So here now we have f of s as s minus sin s, and we have g of s as s raised to power 3. So what are we going to do when you substitute the value of s given from the first one, which is f of s? Let's substitute. We see that we got 0. That is, substitute 0 where we have s and where we have sin s. The answer is 0. Why? Because it is not exist there. Limit is not exist there. And if we substitute 0 at where we have g of s as s raised to power 3, it is also 0. So we now differentiate. That is the fact we already established from that proving. We differentiate. So let's now differentiate f of s. Then we have f prime of s. F prime of s. Differentiate it, we see that we got 1 minus cos s, because by the time you differentiate s minus sin s, differentiate s, we get 1. Differentiate sin s, we have cos s. So that is why we're having f prime of s here as 1 minus cos s. Then we now substitute the value of s given, which is 0. Let's substitute. We still have 0, because 1 minus, if we substitute 0 to where we have cos x, it is cos 0, and cos 0 is 1. That is, we are now having 1 minus 1, which is equal to 0, and therefore f prime of 0 is equal to 0. Then we also look at g of s equal to s raised to power 3. Then we differentiate also. We differentiate g prime of s. By the time you differentiate s raised to power 3, then we got 3s squared. 3s squared. So let's substitute the value of s as s approaches 0, so we now have a g prime of 0 is also equal to 0. So since it is not exist, we differentiate further. So let's differentiate f prime as f prime prime of s. You know, it is 1 minus cos s there. By the time we differentiate it, we now have a sin s. You know that it is minus cos s. So when you differentiate cos, it is minus. So minus minus, that minus we cancel out, then we have a sin s. So f prime prime of 0 now is also 0, is equal to 0. Then we also differentiate that of g prime of s again. We now have g prime prime of s, which is equal to 6s. You know, if we differentiate 3s squared, we got 6s. So let's now substitute the value of s. G prime prime of 0 is still equal to 0. Now, since it is not exist, we now differentiate further again. Differentiate f of s further, then we have f prime 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 of s. Where we have sin s, differentiate it, we get a cos s. So we now substitute the value of s into that where we have cos s, that is cos 0 will now give us 1. F prime prime of 0 is equal to 1 because cos 0 is 1. So f prime prime of 0 is equal to 1. Then also we differentiate g of s again, third time, where we have g prime 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 of s. You know, the g prime prime of s is equal to 6s. Let's now differentiate that 6s. Then we get g prime prime of s is equal to 6. 6s, if we differentiate it, we get 6. So now substitute the value of s, which is 0, substitute into where we have it. You know, since it is constant, then we have gotten the answer here as f prime prime of 0 is 1 and g prime prime of f of 0 is equal to 6. So we have now established the fact that by applying the L'Hopital's rule now, we have the value here until we have differentiated up to the third differentiation. We got it at the third point, so we have a 1/6, 1/6, and here the limit exists. So I think we have come to the end of today's work. We've been able to work on so many methods under the limits of functions of real variables. So we've done a lot on it now, and I believe it is well clear to everyone of us. So we are come to the end of today's work. Thank you and God bless you.